All right, ready to roll? Okay. All right, welcome to Unlocking Efficiency. Got a couple presenters that are going to be talking about that. And also wanted to mention that this room is sponsored by KDM. So they're our sponsor. They're on all the slides. So Curry, Donovan, and Lee, so they're part of our sponsor for today. So I just want to make sure everybody knew that. And also to let you know that a couple things we're asking of you guys at the end of the event today. There's a QR code out there. If you could just do that, and that'll help us for next year, things that we want to do and things that we want to improve for you guys, things that make sense to you guys. So, every year we take all those ideas and all those thoughts and try to incorporate it into the next year's plan for you guys. And also, sometime in 6 to 12 months, you'll receive another survey from NIST. So it's just a survey to help us. The Mass MEP is a center of good standings, and we want to stay that way. And being in good standings helps us get money so we can actually help manufacturers in Massachusetts, so help you guys. So that's our goal. So if you could do that, you'll see that probably 6 to 12 months. You'll get a survey in the mail. And my name is John Grover. I'm a project manager at Mass MEP. I've been with Mass MEP a little over 3 years. So I go out and do projects with clients throughout the state of Massachusetts and help you guys with continuous improvement projects and then different things like that. So maintenance, TPM, you name it, we look at it and help you guys. So I'm going to turn it over to Julia and Ted, and they'll introduce themselves and get us going.
Alright, well, thank you all for joining us. We're going to talk a little bit about additive manufacturing. I'm Julia Toplin. I graduated from Western Polytechnic Institute last May with a mechanical engineering degree, particularly in 3D printing, and unrelated to this talk, but 3D food printing. Not super applicable to most manufacturing workflows, but I now work at AimTech, which is a company out in Massachusetts. I work in reusable silicone masking, which I will get more into later in the presentation.
I'm Ted Green. I also graduated from WPI in May, but not last May. I now work at Wentworth Institute of Technology in Boston, mechanical engineering for the most part, and additive is one of the areas that I've been specializing in for the past 4 years or so. So the plan here is to, first of all, what the heck is additive manufacturing, 3D printing, and stuff like that. So a couple of terminology things. I have some samples we'll pass around and take a look. So this whole world of additive manufacturing is truly what it is. That's the big broad-based category. Rapid prototype, 3D printing is a subset of additive. So the key words here, so additive says 3D model data. So we're talking CAD design, 3D modeling, and then we're producing it layer by layer. 3D printing is indeed additive, but it is using, so we've got deposition of a material through a printhead, a nozzle, or something else. So there's many technologies that people will still say, oh, it's 3D printed. Okay, well, technically it was additive manufactured. It wasn't really 3D printed, but it's kind of like the Kleenex versus the facial tissue. They're kind of one of the things. What I'm going to do is talk about 3 predominant additive manufacturing technologies. We'll say 3D printing, but they're not all 3D printing. The first one is FDM. And FDM can make all sorts of different types of things with it. I'll pass this around. So this was a single print. Many folks would look at this and say, okay, well, how do you put that together? Because it would look like an assembly, but this was just printed as a single item. And then some support material was removed, and we have that. So I have these two, and I'll pass around. But FDM says, okay, we take a filament, which is a round piece of plastic, comes off of a spool, it goes through a print head, which heats it up, forces it out, that print head moves in an XY controlled, computer controlled. And then we have this build tray that keeps dropping down. So we have the XY giving us our positioning. We have the build tray dropping down to create layer by layer. These layers are adjustable depending on what technology, but if you think of a single sheet of paper, about 5/1000ths, or maybe 2 sheets of paper as far as thickness for each of those layers as it's building it up. FDM is the most predominant additive manufacturing. This is truly 3D printing because we do have material that is going through a nozzle. The most predominant one out there, mainly because it's inexpensive. The materials, the equipment needed to do this, pretty cheap these days. And it is most definitely digital. It's all digital control, computer control, stuff like that. And as computers and everything is all the digital world, prices drop down, unless you want to be at the top of the performance. Prices drop down, the equipment drops down, and you can get these a couple $100 on the highest version. One nice thing about this technology, FDM, is I've got this nice little yellow rabbit here, and from the outside, it looks like a completely solid rabbit. And you think, okay, well, let's see the solid, or maybe it was just 2 shells that were glued together, or maybe it was done additively, so it has this infill inside. So we can control how much material is inside of it. If we can control that, we can reduce the cost, reduce the weight of it, and sure, the strength goes down, but you know what? My bunny's still plenty strong enough, even though it's probably only about 40% by volume actual material. Pass those 2 guys around. So this quick rundown of FDM. Oops, I should go the right way. So the next one, and this is kind of in increasing order of cost and maybe decreasing order of prevalence in the world right now, or standards out there. SLA, or stereolithography. So this one says, okay, we've got a laser. The technology still has a build tray that is dropping down. Yeah. Could be going up the other way depending on just who made the technology, but we have this build tray that's moving. And a liquid photopolymer. So we've got a liquid resin, as it's typically referred to. We have a laser, and the laser just hits the resin in certain regions. When the laser hits this photopolymer, it polymerizes it and makes it solid. We make 1 layer of solid, this drops down, a thin layer of the resin is then spread on top of it, and we just keep repeating the process, dropping down and hitting it where we want it to go. Yes, that's the right way. Next one, powder bed fusion. So here, the cost has gone up quite a bit. This gets us into things like this, potentially, metals. My string today. The larger cup there is aluminum silicon alloy. The other one is a stainless steel, and that's a typical surface texture that you get from metal powder bed fusion. This technology, it can either use thermoplastic materials or metals. Same technology, the major difference is the temperatures that we're using here and also the power of the laser. And, well, yeah, the inner atmosphere required or not and what we use in the gases. We've got a metal powder supply on one side. This one keeps raising up. We have something that spreads, again, a thin layer of metal on top of this. Over here, build tray is dropping down, the laser hits it, fuses those powder particles together just in the regions we want. So if we're doing metal, it looks like those. If we're doing plastic, it looks like either one of these. So this is both nylon materials that was done with powder bed fusion, or selective laser sintering is what it's also referred to in the case of plastics. If anybody has any questions at any point,
I have
yes,
a question.
go.
On the metals,
Yep.
how does this compare strength-wise? How does this compare to?
It depends on the exact technology that is used, but for the most part, it'll be, and it comes down to kind of the density of the material, because it is powders, there is some void space in there. But you can expect, as long as it's done correctly, 90% plus as compared to a standard raw material, as far as the tensile strands and things like that. Yeah, what about density? So, and again, that is mainly based on the density. So you can do other things if you really want, for the aerospace applications and stuff like that. They'll take them, they'll print them, and then they'll send them out for hipping, and you'll get the 99 point something percent dense, things like that. But without that, you're in the mid to high 90s as far as densities and strength. Yeah, the formability a little different. All right. So where is it used? Why is it used? Design freedom and part complexity is one of the biggest realms of this whole world of additive. We're not restricted to just things that are rectangular, round cylinders, round holes and stuff like that. We can make any sort of shape we want. And that's one of the biggest things, is trying to convince folks, engineering people, that, okay, standard CAD, you work with your primitives, which are cones, cylinders, and rectangles. But for additive, if we think of like a tree, maple tree, pine tree, any tree you want, it doesn't look like any of those primitives that we use for 3D modeling. It's organic. And we can very easily do that with additive manufacturing. We can make those sort of shapes. It doesn't matter to it. It's just on the other side, how do we design for that? So there's a lot of work going on between the design software, whether it be a Fusion or a SolidWorks or you name it, and how that interfaces with the additive world. Lightweighting, as I mentioned, the parts, the FDM parts, we can have these hollow lattice structures inside. Another example here of just a whole bunch of different types of infill that we can use. So certainly the amount of material and the strength is going to change with each one of these, but the outside is still solid. Part consolidation, GE Additive has really done well with that one. They've taken some of their jet engine parts. The initial one was their LEAP fuel nozzle. It was like 14 parts, down to 1. No more assembly, no more relying on all these different vendors. We've got our additive machine here, we're printing them out, and away we go. They then went on, and there was one particular engine, and out of the number of components that they were consolidating down, it was like 812 individual parts. They got down to 42, just looking at this particular part of the engine. And also it was more efficient, because instead of these cooling channels having to be a straight hole through it or something else, they can make the cooling chamber channels any shape they wanted. So it's a little bit of a game changer. Functional parts, piece I passed around, little on-off toggle switch. There we go, it's functional. I'm not sure what it really does, but it does something. So it is functional.
That's done in one print.
Yep, single print, that's it, done. Someone asked earlier, like, wait a minute, so that was done with that powder bed fusion? All right, just let me back up onto this. One thing about this method is that in the end, this entire print volume is full of powder. And so then we have to say, hey, wait a minute, where's our parts? And we've got to get rid of the loose powder, become a little bit of an archaeologist, get the powder away from it, find our parts, dust them off, clean them off, and like, oh, there it is. So then it's like, well, how do we get the powder out of the inside, leave a hole in the bottom of it, or something like that? So we'd have to leave some sort of a access or an exit point if we wanted to get the powder out of a hollow region inside of it. The other, mass customization. Design freedom and mass customization are two of the phrases that are often discussed with additive manufacturing. And this one says that, okay, mass customization. We can make, I wouldn't make a pen from additive, but if I were to make something like this, I say, okay, well, this one here is 9 inches long. Another customer comes in and says, I want one that's 8 3/4. If we're doing this traditional, like, oh God, I gotta change all my tooling, I gotta go over new molds, I gotta put in an insert. Additive, you say, okay, no problem. 8 3/4. Oh, I'm sorry, I meant to say 8 3/8. Okay, that's fine. I'll change the file and print it out. It doesn't matter. You can make anything because there's no hard, fast tooling setup to the machine. Conformal cooling and heating. Again, we can put these channels, internal voids where we want them to be, and choices of materials. That is still growing as far as what's going on. It depends if we're dealing with the polymer world or the metal side of things, but that does keep increasing. Where is it being used? So design verification and rapid prototyping. So prototyping and testing. So that's where this phrase of rapid prototyping came about a while ago, and it's kind of faded away, but it is an application of additive manufacturing rather than the process of it. So prototyping and replacement parts, jigs and fixtures are probably one of the most applicable ones as far as manufacturing. To actually make this pen additive, no way. Does not make sense. This here, get a box of 10 for $1.50 at the Labor Day sales or something like that. Additive, no. However, something's wrong. You've had some physical deformity or something like that, or an accident, and you can't hold a straight pen. Hey, you know what? We can custom make one for you. It's got a bend to it. It'll wrap around your knuckle and you can hang on to it. Would you be willing to pay $5 for that versus not being able to write? Sure. Yeah, that might work out. So that'd be a mass customization kind of application, or a low volume part. Back to the jigs and fixtures. Pictured here, looking at the quality realm. We've got a CMM machine that we're using. We've got our first article inspection we need to do. We need a fixture to hold it. So sure, we could go through and have the guys in the shop, get the chunk of aluminum, machine it all up, and then you're like, oh damn, I forgot. We were on revision 2 of this. I gave you the print for revision 1. We got to retool. We got to start all over again. Or you just say, you know what? I'll print this out. I'll send it to the printer tonight. Tomorrow morning it'll be ready to go. And then you still say, oh, I still did the wrong one. Well, that's all right. Just send it to the printer again by a little bit after lunchtime. It'll be ready, and then you can actually get going with it. Bless you. I wish I had a picture, but I don't, of something that Lab Tech did in our lab. We have these lab benches, on 4 legs. They have wheels on them, and they're retractable. So they're stationary. It's got a little screw thing on the bottom, and you have less than 180 degrees to get a wrench in there and move this piece. Well, he looked at it and said, hold on, wait a second. We got this thing we can print out. So we printed out probably about 12 inches long, a piece of black plastic with FDM, and it has a bunch of these square teeth on it. You take the square teeth, you run it along this piece that has all these little notches where a wrench, open-end wrench would fit on, and you just go, and it grabs each one of those teeth, rolls it right around, and instantly the table goes up or down, rather than about 15 minutes of moving that 1/16 of a turn at a time. So just simple things like that, not rocket science. Jigs and fixtures also, drill guides. Okay, we need to make these 18 holes. All right, well, we could measure them all off or something, or we can print out a piece of plastic, put in a couple of metal inserts. There we go, our 18 holes. Oh, and that drill guide wraps around perfectly on that part, or it has some other contour to it. The other 2 applications, or the other 2 areas, low volume parts and full production with asterisks here. Lamborghini is using a particular carbon 3D printed parts, carbon, not the material, the name of the company, because they don't make a whole lot of cars. 4,000 a year was their production volume, and they could do that for all of their cars, and they were making an antenna mount and a small bracket, something like that.
Can I ask a question?
Sure.
What about inserts?
What about inserts, meaning?
Inserts, machining inserts. Thousands of dollars on inserts every year. And for the machine
So, do you mean as far as making those inserts via additive?
Yes,
Probably would not be competitive because additive is slower. So, for the most part, if you can buy something commercially available that's done by standard traditional manufacturing, whether it be screw machines, lathes, stuff like that now, to compete, additive is not going to be there.
Okay.
If there's something special about it, or something, the other thing is, in the case of this stuff here, Lamborghini, they said, hey, you know what? We developed this in-house, we printed in-house, nobody else knows what's going on. There's no potential of that IP getting out to the outside world. So there's another aspect there. So they can develop things and keep it totally under wraps. So some of the areas where it's used, automotive and aerospace, not only is it A, so they end up on top, but between skipping the automotive, actually, aerospace and the medical side. That's where additive is being used quite a bit as far as end-use applications. Everybody has hearing aids. Maybe not. Maybe at some point we will. Who knows? But to have a custom-made hearing aid that fits in your ear perfectly, oh, isn't that nice? Yep, that's what's being done. Invisalign teeth retainers instead of braces. Yep, because they all have to be customized. And as far as, replacement knees, hips, joints and stuff like that, sure, there's the generic versions. You've got your size 3, 5, 7. But what if you're size 4? Sorry. Or we'll do all the x-rays, CAT scans. We'll have one custom made for you. Print it out via additive. Come back in 2 weeks. We'll put that in. It fits like a charm because it was made specifically for you. To do that with pens and stuff like that, the cost-benefit analysis isn't there. But if we can make the justification for that extra cost, then it makes sense. Medical, dental, consumer products. So over here, what do we see? Functional prototypes. We see functional prototypes, custom manufacturing. Does it say end-use parts somewhere? Oh, well, that's new product models? No, not so much. So functional prototypes, tools, jigs, fixtures for testing things out. There's one of a slide that I have from a curriculum I go through as far as the class, where a guy's interviewed and he says, yeah, my thought is, don't think, print. Don't think, print? What he really means is, don't keep thinking and designing until you know it's perfection. Because you think it's perfection, you print it, and you're like, oh, geez, I didn't even think of that. It's gonna fit underneath there, how are we gonna get it there? So he's like, no, think about it a bit, print it, try it. We can make these so quickly and easily, we can change it, no problem. Learn from your mistakes, and then you'll come up with the optimum by going through the process. And that's really where the rapid prototyping side fits in. Quick slide here, 3D printing, cost remains fairly consistent if we're doing 1 or we're doing 100. Traditional manufacturing, we're doing 1, it's kind of expensive. We're doing 10,000, that's where things come in. On the other side, traditional manufacturing, says or conventional, we want to start changing around, the pens that are 9 inches, 8.5 and everything, our cost is going up. Additive, it doesn't matter at all. Crooked, yellow, black, it doesn't matter. So it's not a replacement by any means for traditional, it's an additional way of making things. You're a machine shop, you've got a milling machine, you can take a lot of jobs on. You add in a lathe, you can take a lot more jobs. You add in a surface grinder, now we can take on more. You add in additive manufacturing, maybe not on the end-use product side right now, but as far as facilitating things within the shop to make the whole process just more effective, more efficient, more optimizing time and things like that. A lot of worker fixtures, assemblies and stuff like that, where okay, you needed 3 hands to hold this together in order to put the wire on, make a little plastic fixture that does that. It's simple and easy. Process and additive. Side. So an STL file, how do we get there? From a CAD model, or in case of reverse engineering, we can scan an existing part, create this STL file. Let's grab this. Should have done it before. So passed around the piece, so we've got the metal and then the FDM. This was made with SLA technology, and so this. Very smooth surface finish, except that it has all these little faceted regions to it. That is an artifact of going from the CAD model, which was in SolidWorks, it was a beautiful sphere. We then created the STL file. The STL file takes that solid model and converts it into a surface that we can then print out. When it does that, it approximates the surface with triangles. And it looks like rectangles there, kind of trapezoids. We can control that. We can tell it how many triangles to create, or to minimize that. But that was just a nice example of what happens. That only happens on curved surfaces. If it's a flat surface, we can approximate flat surfaces very well with triangles. You create curves and you make them out of triangles, and they get a little weird sometimes. If we're making parts that have overhangs, so this piece here, the black is the actual build material, the white is the support material. And this is the same as this piece here. So if this is being created layer by layer, in order to create the belly of the leopard, right in that region, there was nothing underneath it. I can't go over in an XY and just put a little spot there if there's nothing below it. So what happens is, it fills it in. You can see here that white material is support material. So this support material, in this case, this is dissolvable. This goes into a heated caustic aqueous bath, and the white just dissolves. We are then left with this piece. So all of those pieces were called overhangs, and due to the layer structure, we have the actual part that we're looking for. So that is FDM technology. Other systems, so some systems, that support is dissolvable. In other systems, you actually break it away. Put a little bit in there in order to just build up the regions where you don't actually want material. You need something above it, and then just break that away. And at this point, turn over to Julia. She'll talk about efficiency.
Alright, so as I mentioned, I work at AimTech. I'm just going to take a little minute to explain what we do at AimTech. We do a lot of things, but primarily we are manufacturers of weld wire and alloys. We provide solutions for brazing applications, automated solutions, which are super cool things and I could talk about forever, but not the most pertinent to what we're going to talk about today. I work in silicone masking department, which is kind of this set of 3 images on the bottom. Just a really quick overview of what that means and why we do it. I'm going to use aerospace as an application. It's the majority of the work that we see. In aerospace, you get a part that comes, let's say, out of a turbine, and it's had a diameter kind of erode away over time. We want to build that back up and machine it down to the tolerance called out on the sheet. Very common way to do this is thermal spray. So depending on a call out in a repair manual, you'll take that collection of powders, you'll send it through a system and spray onto a part, and it just through layers build up, and you can machine that down. That's a very oversimplified version of it. But we use masking to cover the parts, but we don't want that material to get built up on. So we will design the mask itself, and then that's great. How do we then make that, right? We make tooling, so we design the mask, and then we design tooling for the negative that we then fill with our silicone material. So our mold tooling is now 3D printing. I want to emphasize the now. So previously, our kind of workflow is, okay, we made the thing, we're going to buy aluminum stock. We're limited in our design because we have to make it machinable in the end, right? So our masks were very simple, and our tooling was equally simple. So you can see a little bit of that negative in here. There's nothing wrong with that. It just became much more difficult during COVID for us to find material, people to do the machining work. So we sat down and we're like, what can we do? We need to make our tooling, and we have to do it quickly. We have turnaround times, and we don't want to make the customer unhappy. So we went to 3D printing. 3D printing has allowed us to design more complex masks because we can do more complex printing geometry. So now it's not a limitation of tooling, it's a limitation of how much support material you can shove on a build plate. So that's been very helpful in our design process. We've had an expanded ability. We can still make super simple things, but we can also make super complex things now too. So 3D printing has generally offered more tolerancing, or at least differently so, as well as it's reduced our hands-on time, right? For a machinist, this was not a manual job, it was CNC, and so we had to make the program, and our engineer had to make the program and then go make the part, and we had to wait for the lead time and the stock, and those all kind of begin to compound. Not to say that there isn't design work for 3D printed parts, there certainly is. But we send it off to a printer, and then we can go do other things in that meantime, right? I think one of my favorite examples of this is that this is a mold that we've recently used. It's seen a lot of wear, so it's been well loved. We laser cut these pieces. We, because of other parts of our business, have a lot of machines at our disposal, but laser cut plates to make that top ceiling space for us. 3D printed rings, I can pass these around. There's a little bit of silicone material in there, but as long as you're not allergic to latex, you should be A-okay. And then we machined this base. this happened in maybe 2 hours, all at the same time. We went to our engineer, we went, here you go, we need this machined. They went, machined it, and in that time we went and laser cut our plates and 3D printed our rings, and the whole job was done in 2 hours.
Could you have printed?
Oh,
that?
yes. So we machined, thank you, I got a little ahead of myself. I got very excited. So our first try at this, so making sure our fitments were right, making sure the product formed the way we'd expected, we actually 3D printed the whole thing. So yes, we started with 3D printing. This I think maybe took 6 hours to make the complete set. Just all in one build plate, hit go, walked away, did other stuff, came back, and gave it a go. We made some design revisions between this one and this one, because we realized there's simplifications we can make as well as simplifications to make it machinable. But generally we started with the 3D printed part. Like Ted was saying, like, oh no, we have no way to fix those metal plates, and now they're coming off as our operators are using them. Let's bolt them down, and there's fixturing differences, but started with the 3D print, and really, I can't ballpark how much this cost, but probably a couple dollars before we then went to a machined piece that is a little bit more expensive, but has a different life cycle. Anyway, thank you. So yes, you can print them. We actually use a lot of different materials. So this white is a different material than the black piece that's going around. It is less expensive. This is just a really basic plastic. It's PLA, which is corn-based. The black pieces that have been going around are nylon with carbon fiber microparticulate. So it has much more increased mechanical properties and a longer life cycle. So when we get into high run parts, let's say 1,000 pieces and above, we'll use a more robust plastic. But for prototyping, something like this is sufficient. This was used maybe 10 times and doesn't really look all that used. If we get 1,000 parts of this, yeah, maybe we'll think about a machined variant, but this is also not designed to be machined. So printing has definitely allowed us to kind of reimagine and rework how we approached our masking. It's reduced our lead time. Ordering spools of filament have a lead time of maybe 3 days if you're unlucky, rather than a longer lead time with most. Oh. The lead times of most common sheets of metal. I think also something to talk about is cost. There is some upfront costs, right? You need the printer. If you don't already have an active CAD software, you'll need that investment along with the PC that can facilitate that. But let's assume for all intents and purposes you're able to CAD, you're able to pull STLs as Ted was sharing earlier. It surprisingly, or maybe not surprisingly, isn't always the most cost-effective to 3D print. So if we take a look at mold sample 1, which is this upper bound, I don't have a sample here, but it would be about $4,300 to make that out of aluminum stock. That factors in our machinist time and lead times and everything. But to 3D print it, just shy of $2,000. I should mention with 3D printing, you often have a little bit more of a constrained build volume, so you're splitting things up a little bit. So there's a little bit more fixturing involved, or at least for us. So in that example, it's more cost effective for us to print it. But there are times where that's not true. So for this bottom piece where it's much thicker, much more dense, it actually ends up being a lot less expensive to machine. Granted, the internal geometry is much simpler, so the overall machining time is greatly reduced, but it actually costs more to 3D print, even though it's, in a different example, more cost effective. So it is a little bit of figuring out which applications are best for you to 3D print versus machine. It's not a replacement, as Ted is saying. It can be, let's say, okay, you're booked for 3 weeks, but you need a sample. 3D printing can be a great, in between for that. But there is still areas where machining is the optimum choice. Now, I've talked a lot about the stuff that I work on because I think it's super duper cool. But we do other things, and we do 3D print other things like process improvement. So this is the back of one of our job, we had to cover it. I can't really explain why, but we had to cover the exit of our lathe, so that's a 3D printed part, and it's been in that lathe for almost, I think, a year now for this job, and it really hasn't degraded. That was a material choice, that is a consideration, but it's running great. We also have jigs and fixtures, so this is part of our automation solution, but we had to have a very complex geometry to fit that part, and we bolted it to a machine plate because we needed rigidity on the bottom. So you can kind of, you know, pick and choose which ones are best to machine, what parts are good for 3D printing. You know, it's very variable. I think that's one of the beauties of 3D printing too. It can integrate a lot with what you already have going on. I think that is most of what I have to say. So if folks have questions, I don't know where else I'm supposed to talk about the slide. I will leave it to Ted. I think you're a little bit more knowledgeable in the courses.
So the last slide here. So through Mass MEP, they do have a course that is available, applying additive to your manufacturing. And it's typically set up as a 3-day program. So the first day would be on site in your facility, taking a walkthrough, seeing what's going on, what are some of your potential pain points, or just looking around saying, hey, wait a minute, if that could be 3D printed and offer this particular advantage. Going through in a little more detail, I hit 3 of the technologies pretty quickly. There are several others. And then looking at the design side. So designing for parts that are going to be 3D printed. One thing is you can do a lot more, but then also knowing, well, just how would the CAD design work out best in order to accomplish that is part of it. Then there's making up some prototype parts, whether it be, as we discussed earlier, or something, or as was discussed during that first day, or something else that you had in mind. And then the third day would be a trip to a lab, either in Amherst, Mass, or Boston, where there's a fair number of different 3D printing technologies, so you can actually see the equipment, kind of get a hands-on look at it. I would say work with it, but you don't really work with the equipment because you just send it the file and hit the go, and it takes it from there. So that is available. And Ellen or others in Mass MEP would have more info about that. At this point,
Any questions, anybody? If you have some questions that come up and you don't think of them now, grab a business card, you can email me and we'll get an answer back to you. If there's anything that comes up or anything that you're thinking about or need clarification
What
on.
about different materials? Like I manufacture drumsticks,
Okay.
and I've always like dreamt of what if we could print one? You know?
So,
There are
what would
wood
you,
embedded materials, like you can get
There are some.
wood particulate embedded, and I think it's PLA right now.
It's one of the plastics. So the material side, it's constantly evolving. And
Right.
different companies are coming out with different things. Some of them are very much mainstream. The FDM, the fused deposition modeling, plastic ones here. These are all traditional injection molding thermoplastic materials that were just made into a thin ribbon to create a spool. So this is ASA or ATS plastic, which one this exactly is. But there are other companies who are doing things who are kind of off the beaten path.
Yeah, like making hammer handles out of sawdust.
Yeah, exactly. So it's if you can pulverize it and if you can put it into some sort of and most of the time it would be with plastic or some type of a plastic material polymer, such that once you heat it up, you can shape it and form it, then there you go. So drumsticks would be an interesting one.
Yeah.
But why could they be made of plastic? They, especially if you went with, imagine, just think for a moment here, a drumstick, I'm picturing, however long it is.
It's pretty much 16 inch.
16, but what if somebody wants a 14-inch one? That's a special. But what even better, with FDM, you could control the density along that drumstick.
Right.
So
is
in
there a
one case-
resonance quality to it? Because that's why drumsticks are used from wood, because there's a tonal.
Well, I think tonal quality, if I'm thinking of wind chimes, it depends on the diameter and the wall thickness.
Well, it's also the thickness, it's the density of the wood itself, the cellulose fibers. So,
Which could
I'm
all,
just
yeah,
something I'm thinking of.
which could be modified because if I look at, so this piece here is obviously a lot of that is hollow.
Right.
This piece here, everything we see that is plastic, this is the nylon material. this is solid inside of here, there is no infill. So these are gonna have totally different qualities as
Right.
kind of you're talking about, but you can control that totally. Whereas now with wood, maybe you can switch from, a maple to a birch or something, but
Hickory and maple.
yeah, okay. But you can't control the density of that wood,
No.
whereas here you could. You'd be onto a whole new realm right there.
Yeah.
Which I hadn't even thought
It would
of.
just be like added to the product
Mhm.
category.
Yeah, so it's,
I don't know,
and that's it.
I've thought about it.
So it's things like this, of thinking about what can be done, or what can additive offer to it. To just try to make a drumstick through additive and have it be the same thing, probably be better off just sticking with your hickory maple.
Yeah,
But
right.
if, like I said, we can alter the density, get some different, one's for the jazz band, one's for the rock band, different weights in different
Oh,
areas.
yeah.
Yes.
So Mass MEP, we do work with many 3D printing companies where if you wanted to say, hey, I have a drumstick and I want it to be made out of 3D, and it has to have these properties, we can get it printed for you. They use the universities, to use the students, and they design, modeling, they do everything. Yeah, so if you're interested.
No, I am interested.
Yeah,
absolutely.
yeah, we can reach out to one of these universities that we work with. They do it at low cost, sometimes no cost. They do it for fun of it.
It'd be interesting just to see what it would do.
Yeah.
And I'm sure the technology and everything changes on a weekly basis.
It's digital, so yeah,
Yeah.
just like with everything digital, it just keeps ratcheting
Right.
up, or I don't know if it's ratcheting up, but it keeps moving. So,
Right, yeah.
sure.
It's different. Yeah, okay, well, thank you.
Also, like Alan was saying, Mass MEP is gonna have a 3D printer in our office within the next 2 months that we can do some things for you too. So do some prototyping and things like that as well.
Printers.
Not Forge.
Forge.
Oh,
Oh, not Forge.
oh, the black material, yeah.
Any questions? Yes.
With regards to strength of materials, with subtractive manufacturing, which is sure. We have ASTM specs, for example, you go to the book, you see that 316 stainless steel has certain tensile limitation, minimum requirements. Is there any type of specification in development that would be coupled with additive, specifically to metal manufacturing, so that as these items are built, maybe there's a one orientation that gets built at the same time that other things in development like that?
Yes, there most definitely are. ASTM F42 subcommittee has been into additive for a while, and those initial two terminology definitions between additive and 3D printing, those are from the ASTM F42. But there's been a lot of work within that subcommittee on doing things just as you mentioned, because there are differences based on orientation. So, and how do you, that's part of the designing of it, is how do you optimize that for what you're trying to do? Are you trying to optimize for cost and time, or are you trying to optimize for tensile, or is it more the flexion characteristics of it? Like that. It will change things.
Does it seem like it's guiding towards printing the article, the test article alongside the production item?
Yeah, a lot of times that is when it's done. If, for instance, on any of the medical and or the aerospace, if they're setting up, it's going to be most likely a metal powder infusion system, and they will print out coupons in a couple of different orientations as part of the lot or the batch control for that particular one. Test a couple of them and save a few. And that way. There is still work being done as far as the repeatability, testing, and quality, because I would say it's a relatively new technology, and that's really true. The initial patents were the early mid-80s, so it's been around a while. But as far as the commercial applications and acceptance of it, that's the relatively new one. And I think a lot of that is because, as we said, things are changing weekly in the digital and in the computer control side. And it wasn't until all of that came together that we could cheaply, accurately, quickly have control over all this XYZ positioning in order to make the equipment of a low enough cost. cost, that it became feasible. So in this now it's just really taking off for all sorts of ways. So it is definitely here to stay. It will grow. It's just it's not going to take over traditional manufacturing. It's going to, like I said, instead of a surface grinder, it's going to be an additive to do these sorts of things.
Okay. We're there.
Oh, time-wise?
Yeah.
Oh, yeah, that's fine, yeah.
That's okay. So we still got a couple minutes in between
Yeah, yeah,
sessions,
we have time between the sessions.
Thank you.
Thank you. Look at your cards.
It's okay, they always look the same, you know.
Thank you.
So for us.
Don't worry about it.
Thank you.